All right, let's dive right into one of the biggest questions in all of physics. Is Einstein's theory of gravity, the final word? I mean, for over 100 years, general relativity has been a monumental success. But there's a huge catch. To make the math work, we have to assume that almost our entire universe is completely invisible. Now, though, with the incredible power of the James Webb Space Telescope, we can finally run a high-stakes test that could point the way to a whole new understanding of gravity itself. So, let's follow the clues.
And this, right here, is the heart of the whole problem. Our absolute best theory of gravity only matches what we see out there in the cosmos. Galaxies spinning, the universe expanding, if, and only if, we invent two totally mysterious things: dark matter and dark energy. Together, they're supposed to make up a whopping 95% of everything. But here's the thing. We've never detected them. We have no idea what they are. And that forces us to ask a really radical question. What if? What if they're not there at all? What if the theory of gravity itself is what's incomplete?
So in this explainer, we're basically going to be cosmic detectives. First, we'll examine the cracks in Einstein's beautiful theory. Then, we'll introduce a wild new suspect, the vacuum of space itself. We'll uncover a unique, testable prediction it makes, see how the Webb telescope is finally putting that prediction to the test, and then we'll look at the very first clues that have just come back from the early universe.
Okay, so let's start at the scene of the crime. For a theory to be challenged after a century of just knocking it out of the park, well, the evidence against it has to be pretty serious. And for general relativity, we're not talking about minor little glitches. The problems are deep, they're fundamental, and they really suggest something huge is missing from our picture of the universe.
Here's the case file. First up, to explain why galaxies spin so fast without flying apart, general relativity demands that they're all nestled inside these giant invisible halos of dark matter. But we've never found a single particle of it. Second, to explain why the expansion of the universe is speeding up, it needs a mysterious dark energy that's pushing everything apart. We have no clue what that is either. And maybe the most damning piece of evidence? The theory literally predicts its own failure. At the center of black holes and at the very beginning of the Big Bang, the math goes to infinity. It creates things called singularities. And that's basically the laws of physics screaming, "I don't work here. You need a new theory."
So these cracks have led physicists to explore some pretty wild new ideas. And one of the most compelling is called vacuum field theory, or VFT. Now, this isn't just tweaking Einstein's equations. No, this is a totally different way of thinking about what gravity actually is. It suggests that gravity isn't about space-time bending, like Einstein said. Instead, VFT proposes that gravity just emerges from the behavior of the vacuum of space itself.
In this new picture, the vacuum isn't just an empty, boring stage where physics happens. No, it's a physical, dynamic thing. The theory treats the vacuum like a medium that can be pushed around and distorted. And what we feel as gravity, that's just the effect of those distortions and flows within the vacuum. It's a massive shift in perspective. A simple way to get your head around this is to imagine space as a kind of cosmic fluid. When you drop a massive object into it, it doesn't bend space-time. Instead, it creates pressure changes and currents within this fluid. So gravity is just the effect of these currents pushing things around. This idea also neatly gets rid of the singularity problem because it says the vacuum has a maximum density. You can't just squish it down to infinity. And it explains why galaxies behave so weirdly, not by adding invisible matter, but by suggesting that this vacuum fluid itself just acts differently when accelerations get really, really low. Now, any good scientific theory can't just solve old problems. It has to make a brand new, unique prediction, something you can go out and test, and maybe even prove wrong. And this is where vacuum field theory gets really, really interesting. It makes a stunning prediction that connects what's happening inside a single tiny galaxy to the expansion of the entire universe. This is its smoking gun.
Okay, don't let the equation freak you out, because what it's saying is profound. On the left side, you've got A0, A0. You can think of this as a kind of magic number, a specific acceleration, about 10 to the minus 10 meters per second squared, below which gravity seems to get a little bit stronger than we'd expect in galaxies. Then on the right, you have h of z, the Hubble parameter. That's just a measure of how fast the universe is expanding at any given time. What VFT predicts is that these two numbers aren't just a coincidence. They're physically, directly linked. It says the local physics inside a galaxy is being dictated by the global state of the entire cosmos. It's a wild idea.
And this right here is the heart of the debate. In the standard model, this A0 number is just a fluke, a coincidence that pops out of complicated dark matter simulations. It doesn't mean anything deeper, and it's assumed to be constant, the same value everywhere at all times. But in vacuum field theory, A0 is absolutely fundamental. It's a core property of the vacuum itself.
And because the universe is expanding, VFT makes a unique, falsifiable prediction. A0 is not constant. It should have been larger in the past, and it should evolve over time, changing in perfect sync with the universe's expansion rate.
For decades, this has been a prediction just sitting on a shelf, totally untestable. I mean, all the galaxies we could study in detail were right here in our cosmic backyard, where the expansion rate is pretty much the same. But that has all changed. The James Webb Space Telescope is our new detective on the scene, and it's so powerful it can look back in time and investigate galaxies from the ancient universe where the expansion rate was completely different.
So, what makes Webb the perfect tool for this job? Well, its incredible sensitivity means it can collect the super faint light from galaxies billions of light years away. But even more important, it can do something called spatially resolved spectroscopy. That's a fancy way of saying Webb can measure the speed of different parts of a galaxy at the same time. It doesn't just see a fuzzy blob, it can build a detailed speed map, showing us exactly how the stars and gas are moving around.
So, the method here is actually pretty straightforward. First, astronomers pick out a bunch of distant galaxies from different moments in cosmic history. Second, they use Webb's NIRSP instrument to carefully map out how fast each part of the galaxy is rotating. Third, they add up all the normal stuff they can see, all the stars and gas, to calculate the galaxy's baryonic mass. And finally, using that rotation speed and that mass, they can actually work backwards and figure out the value of A0 for that galaxy at that specific time in the universe's past. And if you do this for a bunch of galaxies at different distances, well, you can literally plot how A0 has changed over cosmic time. You can compare the data directly to the predictions. This is the moment of truth. And a team has done exactly this with an initial sample of galaxies. The verdict from the early universe is in.
So what did Webb find? Does that magic number A0 stay constant through time, like the standard model assumes, or does it evolve right along with the expansion of the universe, just like vacuum field theory predicts?
Okay, let's look at the evidence. On this chart, the further you go to the right, the further back in time you're looking. The vertical axis is the value of that acceleration scale, A0. Now those black dots, that's the real data. That's what JWST actually saw. The colored lines are the predictions. The red line is what you'd expect if A0 is constant, like in some other alternative theories. The blue line is the prediction from vacuum field theory, and the green is an approximation for the standard dark matter model. So the big question is, which line do the dots follow?
Let's look at this another way, just to be crystal clear. This plot shows the ratio of what Webb observed compared to what vacuum field theory predicted. If the theory is right, all those data points should land right on that dashed line at a value of 1. And just look at that. With one outlier, the data from these incredibly distant ancient galaxies clusters almost perfectly around the VFT prediction. It's showing that the values are tracking the expansion of the universe almost exactly as the theory said they would.
Now, for comparison, what happens if we plot that exact same data against a theory where A0 is supposed to be constant? Well, you get this. If that idea were correct, the data should cluster around 1. Instead, it's a total mess. The ratio just gets bigger and bigger the further back in time we look. It's a dramatic failure. This data pretty clearly shows that a constant acceleration scale is just not what's happening. The observations tell us A0 was much larger in the early universe.
Now, while these first results are frankly mind-blowing, we have to be good scientists here. This is just the beginning of the investigation. As the researchers themselves point out, there are still uncertainties, especially in getting the exact mass of all the stars and gas in these super distant galaxies. So this isn't a final verdict just yet. Think of it as powerful, tantalizing new evidence. To really nail this down, we're going to need a much bigger sample of galaxies. But wow, these first clues are all pointing in a very fascinating direction.
And that leaves us with this final, really provocative thought. For decades, we have been hunting for exotic new particles to solve the universe's biggest mysteries. But what if the answer isn't some new particle at all? What if it's been all around us this entire time, hidden in the dynamic physical properties of empty space itself? This brand new evidence from Webb suggests that the vacuum may not be a void after all. It might just be the very engine that drives the cosmos.